Good afternoon, everybody. My name is Pablo Mendoza. Welcome to our Water Resources and Environment webinar here at Universidad de Chile. This is an activity organized by the Department of Civil Engineering. So today we have Mrs. Daniela Henry. Daniela is a civil engineer with specialization in hydraulic, sanitation, and environment from Universidad de Chile. She also holds a master's degree in environmental sciences at the University of Vienna, Austria. She's a pre-doctoral researcher at the Catalan Institute for Water Research, and she belongs to the Water Science and Technology program at the University of Girona, Spain. Daniela, we're very happy having you here, and the stage is all yours.
Thank you. Thanks, Pablo. Thanks, Nico and Kathy, for inviting me today. Thanks, everyone, for being here. So, as you already know, my name is Daniela Henry. I'm a former student here in the faculty here in school. And I'm going to talk to you a little bit about what I've done and what I'm working today on. And I'm going to bring to the table a topic which I found very interesting, and maybe all of the ones that are trying to deal with modeling right now will agree with me. So it's about the current status and the challenges in modeling carbon formula. Probably if you are modeling in another research field, you will find many of these challenges familiar. So first I'm going to talk a bit about my personal, professional actually background. Then I will show
Dani,
you. Yes.
tienes que compartir pantalla.
Very important.
Y hablar un poco más cerca de la mesa, por favor.
Ok.
Gracias.
¿Es este el número 2?
Ahí lo estamos viendo.
Sí, de punto. Puedo seleccionar aquí. Estoy aquí. Ajá. Okay, do you see my outline?
Sí.
Sí, lo estamos viendo.
Yes. So first, my personal background. Later, I'm going to show you which is my project I'm working on. Our project is called Invent Water. The motivation for studying what we are studying right now, and the topic itself, which I'm going to talk, is the current status of carbon burial modeling and the main challenges we find when we want to deal with it. And finally, I'm going to close up with the future direction. So, as I already mentioned, I'm a former student from here, from the civil engineering faculty, and I studied the specialization of hydraulic, sanitation, and environment. My final project was with Professor Catherine, which is here with us today. She invited me, actually. So we work with the arsenic removal from contaminated water using two different kinds of supporting material, and we studied experimentally the capacity of this support material to remove arsenic. And we also applied at a lab scale in constructed wetlands. Later, I worked for a couple of years in the consultancy industry here in Chile for a couple of years. I modeled and designed irrigation channels for public projects. Some of them were for farmers in the north of Chile. And also I worked with a company, with an environmental consultancy in Australia. We were monitoring the environmental impact of quarries for the neighbors. And so we were monitoring underground vibration, dust, noise, and also the water quality of the pit itself and the surroundings. Later, I did my master in the University of Vienna, the Environmental Science Master, where my final and main project was to study the influence of water quality parameters on methane evolution emissions in the reed belt of Lake Niceville, Australia. So the methane emissions are, evolution emissions, is one of the pathways how emissions can be released to the atmosphere. So we have the diffusion pathway, we have the evolution emission, which are mainly the bubbles that are emitted directly from the sediments to the air. And also we have the transmission from plants. So we study this specific pathway in this very particular ecosystem in Australia. So there is where I started with this project. So I was hired as a PhD student candidate, as a pre-doctoral researcher in the Catalan Institute for Water Research, and I'm registered in the program of Water Science and Technology. So this is our institute, and these are my main supervisors. They are, the three of them are specialized in biology and in different aspects of the carbon dynamics. And the project Inland Water is 15 of these small projects. So I'm one of them, and there is other 14 PhD students all over Europe. But we are all working under this project, which is meant to create inventive forecasting tools for adaptive water quality management to a new climate. Our project in particular is the number 13. You can find more information in our website, Inlandwater.com. And the name of the topic is forecasting feedbacks between the climate system and carbon dynamics in lakes and reservoirs under adaptation scenarios. So the motivation to study first the carbon cycle. Lately, the awareness of studying the climate change has made very important to understand where is carbon reallocated in the different compartments of the Earth system. So that's why it's so important to study the carbon cycle. If we look at it at the ecosystem scale, which is the left side picture, we see in a very simple way the main processes that are involved. So the water body receives the carbon load in the sediments and the organic matter. And then this can be sedimented. It can stay in the sediments and be buried there. And that is what we are going to call the carbon burial. Or it can be mineralized by microorganisms or resuspended and stay in the water column. When neither of these happen, this can be, the carbon can continue downstream and go to the next, to connect to the river network or other ecosystems. If we look at it at a global level, I like this diagram, which might look a little bit difficult or complex, but it's nice because it considers compartments that are not normally considered when we see these diagrams of carbon budget. So here you can see how on the left, right, everything started in terrestrial system and finished in the open ocean. This is what is normally called the land to ocean aquatic continuum. But then we also see two smaller loops because there are other interactions in between the terrestrial ecosystem, for example, and inland waters. Then it can be again released to the atmosphere, go back to terrestrial ecosystems, or go back to the open ocean. And the same interactions occur between the open ocean and other ecosystems as estuaries, tidal wetlands, continental shelves, water, etc. In red, you can see the influence, the anthropogenic influence. So all these ecosystem, lakes, reservoirs, wetlands, and coastal ecosystems are vulnerable to climate change and other anthropogenic perturbations. So with climate change, air temperature has risen. There are changes in patterns in precipitation, and extreme events are every time more frequent. Also, we have modified the use of the lands. So deforestation, fires, and the building of reservoirs have modified the sequestration capacity of these ecosystems because we changed the vegetation type, the cover, the vegetation type and cover, and also because we changed the hydrology of the system, which altered the carbon transport. So these environmental impacts will probably increase carbon emissions from water bodies, and increasing the emissions normally means that there will be a decrease in carbon volume. So the rising temperatures normally means increasing the mineralization and the methanogenic processes, but also carbon sinks can be damaged because of erosion because of erosion, sorry. And this will release directly the carbon to the atmosphere. So our focus in particular is to study the role of reservoirs in the burial, the carbon buried in the coastal ecosystems. This is normally called blue carbon, the carbon that is contained in this coastal ecosystem as mangroves, seagrasses, and salt marshes. So we want to analyze how much the effect of the retention of the dams actually affect the later carbon burial, because also in reservoirs there is a sequestration of this carbon, but there are other processes there which might make the carbon less stable there, or maybe more, we don't know. So why use the modeling tool? Because it's a powerful tool to engage the knowledge of cross-disciplinary studies, such as the study of carbon cycle dynamics. So what is happening now with global carbon modeling? So first I wanted to mention that the actual role of carbon burial in inland water was not considered until lateral fluxes were incorporated. So connection between these ecosystems. And even now that some of them incorporated river networks and other inland waters normally are seen as mere pipelines. So they just transport carbon. Inland waters as reactors at the ecosystem scale have been included at the ecosystem scales many times, but not yet in Earth system models. There are great uncertainty about carbon burial drivers and processes. And so far as we know, there is no model which integrates terrestrial, freshwater, and coastal ecosystem, considering burial processes in all of them. So here we did a literature review. We found this 9 model, which we found relevant for studying carbon burial at a large scale. I'm not going through all of them. I just wanted to see that there are a huge variety of model types, spatial and temporal resolution, the programming language that they use, or the compound that they model. So this takes us to the when we did this literature review, we found many challenges. So we found several models which could simulate this carbon transport and transformation at a large scale, but yet there is great uncertainty and other major challenges, which we enumerated as lack of integrated vision, disharmonized technology, relevant processes differ between models, there is a lack of data, and there are challenges in spatial and temporal cross-scaling. All of those will bring high uncertainty. So I will just quickly go through all of them. So as I mentioned before, there is no model which integrates all these ecosystems, so terrestrial, inland waters and coastal ecosystems, they normally, even if they are considered to be a land to ocean aquatic continuum model, they go from the terrestrial system to the river mouths normally. So this is the coastal ecosystem is just considered as a receptor of the carbon, and processes there are not modeled. So this is mainly because the complexity and heterogeneity of the coastal ecosystems. So far, there's been a great effort at mapping those ecosystems and characterize them, so we can see how much we have lost from those ecosystems or gained, but not yet. They have not been included in global carbon. And also, there is the compartmentalization of study fields, because they are, you can see that there are big difference between the marine ecosystem, the terrestrial, the inland water. So they need to mix and work together to consider a way to transmit outputs and findings in transversal way. The other big problem that you find when you address the literature is the Disharmonized terminology. Just for our main parameter, which is the organic carbon movement rate, we can have it defined as organic carbon sequestration rate, organic carbon mass accumulation rate, carbon accumulation rate, a specific deposition rate, or you can even find it just as stock without considering the amount of time that has been there. And then we have other concepts like linear sedimentation rate, which are called like that in the inland water studies, but if you go to coastal or wetland studies, you will see it as sediment or even soil accumulation rate. Then there is sedimentation rate, which is also called mass accumulation rate, things like that. So we know that in every modeling exercise, we will choose our assumptions according to which scale we are working with, temporal and spatial scale. So this normally implies that we will leave behind some processes that are not, we will consider that are not relevant or will add too much complexity to our study. So here we have the same 9 studies that I mentioned before, and we did a little table in order to be able to compare them. And we name the different processes and check and study if they consider them somehow in the model. So here we can see that in 3 of the models, carbon burial is not considered. We add them here in the list and in the study because we think that they are potentially useful for studying it, but they have not been included yet. And also there are 4 of the 9 that don't consider sedimentation, neither as a process or as a parameter, as an important parameter that can derive carbon movement. The other challenge is the lack of data. This is the most common challenge of all. And here we did a little update of the organic carbon burial rates, which exists in the literature nowadays. Probably we don't have them all, but at least the most important studies, or most of them. So in the different colors, you can see the different ecosystem types, lakes, reservoirs, plains, and the coastal ecosystems. And the size of the dot is the level of carbon burial, the rate, sorry. And here in the bottom, I add the formula, which is normally the methodology that they use to calculate this rate. It varies a lot between studies, and also how they calculate each of those parameters also varies. So they have different methodologies to measure. For example, linear sedimentation rate is the depth of the sediments which accumulate in the bottom of the water body during a certain period of time. And this can normally is calculated using isotopic dating. But some studies use one isotope, some others or some others just use bathymetry, for example, to calculate these depths. So these make the studies and the transferability of the data also very difficult. Then there is the DVD, which is the dry bulk density that you need to measure on site or have an estimation of it, and the organic carbon. Another challenge is the spatial and temporal cross-scaling. So upscaling from site measurements to regional or global simulation brings uncertainties related to the spatial heterogeneity and the processes occurring at different timescales. Also sediment deposition heterogeneity, geomorphic settings, and the consequent heterogeneity on the carbon burial. So this also happens temporally. Processes can happen at minutes, in particle settling or heterotrophic respiration, 2 years or centuries when we are talking about carbon burial. So I just gave some examples here where Peter and others say that large range of organic carbon burial rates in salt marshes generates uncertainty in upscaling measurements. So this condition the costs of restoration and conservation of those environments. And Hanson and others said that the nature of lakes affects the upscaling of restoration estimation from laboratory experiments to the regional scale, because there are critical components like temperature, oxygen, and light that vary extremely in spatial and temporal scales. So finally, the high uncertainty, that is mainly because of all the challenges mentioned before. So every model approach will be defined because of the temporal and spatial temporal of need, and according to the knowledge extract the resources and the data availability. Each approach will carry uncertainties which needs to be addressed, acknowledged, and somehow quantified. Every assumption we make related to burial processes will influence the outcome, and the little amount of observation and the poor understanding of carbon burial processes are not enough to cope the uncertainty. So uncertainty should decrease with time because we are developing models, and we are every time incorporating more and more data to our data set. But even so, we need an interdisciplinary integration that will reduce the sources. So just to wrap up some comments about future directions and conclusions. So we know that the awareness of climate change is increasing. And so it's also, there is a need to understand and increase our carbon sequestration capacity of ecosystems. And this is an opportunity to continue improving the quantity and quality of our measurements in order to use them broadly in various fields of research. In my opinion, it is a waste of resources to build data and not be able to transfer it among studies. So harmonizing the terminology and methodology is necessary. Huge steps have been taken in technology and computing capacity. So it's time that we use these and take advantage of the open science community. So that's the message I wanted to share with you today. I'm open to questions or to discuss things.
Okay. Thanks a lot, Daniela, for your seminar. That was very interesting. So first, I want to ask Nicholas, if you're there, do we have any questions?
No yet.
YouTube or from Zoom?
No.
Not yet. Okay. I have several questions for you, Daniela. So the first one is related to one of your slides where you mentioned about relevant processes. You said that relevant processes differ among models. So the question is, for which process you have found that there are the largest disagreements among models? Is there a particular model that the models can really differ, not only whether the process is included or not, but in terms of how the process is modeled, what equations are used, what are the assumptions?
Yes. Well, talking first about Korea, it is very different. Some models or some studies just, for example, consider it as a percentage of what it is, what is not needed, for example, or a percentage of how much is received, or they have like an empirical model behind. It varies a lot of the assumptions they do. And also, for example, respiration, some or mineralization. Yeah, I will explain which are the assumptions of each of them. But for example, some consider the net ecosystem production, some others calculate the biomass production, but it's quite different. Yes. For us to determine to say this is respiration, yes or not, we need to specify why are we saying not respiration, because maybe it is included somehow in an indirect way. So it's also hard to say if they are included or not, because sometimes they include it very physically. Yes.
Okay.
So,
okay. Thank you, Daniela. And which one is the most challenging from all the processes in the carbon cycle? Is there any particular process that is really hard to model, to include in models? Or from your perspective, which one do you find that is like super hard?
Yes, I think carbon border has, because to measure it, you need to go in the field and take a core and calculate it, and that's not something that is normally calculated. I would say that, for example, emissions it's more in the routine of going in the field and measuring, but not burial. I would say that burial is one of the, and it's why they are not including most of the time. Or for example, in rivers. In rivers, normally they just, if they consider it, it's normally as a meter. And you know that in a river, if there is a meandrous river, deposition is important and burial should be important. But normally they are just as a pipeline.
Okay. And I think that you made a point towards my next question, if you don't mind, which is related to data. So what kind of data do you typically incorporate in order to develop this type of model?
There is like a basic data that you need. You are trying to study the feedback in the atmosphere, so you know climate model that you can maybe couple with your model. Climate. You also need data from the sediments. Normally, you can find products related to the soil. For example, when we talk about density, carbon content, there's a lot of data. Talk about the terrestrial part of the soil, but it's hard to find data in the sediments, in the riverbeds, in the lakes. And then you need this the sedimentation rate, layer of data that one you just need to.
And have you had the experience of collecting What kind of data?
The course, yes,
Yeah.
the segment course, yes.
And is it
Yeah.
too challenging?
There are many things because normally there is also resources limitation. So if you go, you can take maybe 1 or 2 courses from a lake, but you know that the lake is super clean, and you need to properly select where you want to, or where you can access, because if you have a lake of 50 meters depth, it's very hard to collect 74. So you have the other problem, which is it's infinity in the same ecosystem that you mentioned. So I would say it is something that you can say, okay, every month we go and take 5 samples of it. The work. It's not easy.
So how often do you need to go?
For me,
Anybody?
yeah, but also the problem is that there are lakes that are super hardly studied, and everyone just studies there, so you find a lot of data there. But you can see in the map that there are places where nobody took samples. We don't find it in the literature. That's also a problem. If they are there and we cannot find them, that's also a problem. In Africa, in North Africa, we don't have any measurements. In South America. So I think anything or start doing.
Thanks, Daniela. Do we have any further questions from YouTube or from our audience here in the room?
But let's see if Nicolas has some.
No. There are no
Okay.
questions. Yeah.
Okay, thanks, Nico. Kathy?
Yeah, it seems, congratulations, Daniela, on your amazing work. It looks very hard. Since you're showing that map, and as you just said, South America is blank, and especially Chile is blank. So I had some questions about the data as well, but how to understand, I want to understand how global is your model, or it's going to be, how applicable will be for zones, for example, Chile, Argentina, Bolivia, or Peru, where you have 0 data to calibrate or validate, so compared to Europe, where you are. So how will you handle this lack of data to develop your model?
Yes, actually, the model can slightly not being calibrated with the measurement data.
Okay.
Because that's the reason, it's not enough. So we need to deal with that and integrate it to the uncertainty of our model. We can use it maybe for comparison to see that we are having reasonable results, but we cannot calibrate the global model with this amount of data.
Okay, so you will only use this data as a comparison,
Yes.
like a reference.
Yes. But I needed to collect it to see if it was enough or not. And it also can give you much information about it. You can go deeply and study each ecosystem type, for example. You can also gather all the information from this data, not for calibration.
Okay. And what you said about the ecosystems, the coastal ecosystems, right?
Mm-hmm.
You said that it's very complex because there are different processes. But I was thinking, maybe it's not worth it. I don't know if you have the answer yet, because sometimes if you have, let's compare with the arsenic, for example, if you have different routes, and this case you have different routes for the carbon. I'm not sure, but I'm sure if you can say it or I didn't get it. If that's main sink, it's an important source for the boreal, the coastal ecosystem, because if they are not, maybe it's not worth it to fight or to understand. Yes, but to include it in the model, maybe it's not worth it. So how important is the role of these ecosystems in the total burial? Or does it depend on the zone? Or does it depend on what? So maybe in some cases you can consider them, or maybe not, I don't know.
Yeah, I would say that they are important because they are also one of the main exports into the open ocean, and also in the ocean there is a big space for carbon burial. So I would say it is important to study it. And Also, there is a lot of autochthonous generation in those places. In this vegetated system, you have generated carbon there. So I would say it is important to include them and to see the whole picture to decide if they are relevant or not at the end. But our main objective is to study how the reservoirs influence that amount, because we know that 50% of the carbon is tamed. And so I think that's a big number.
Okay, so the main focus is on the dams, on the reservoirs.
Yes, and to see the different, what happens if they are there and if they are not there. How this influence the carbon border.
Okay, but are you more concerned about what already happened or what's going to happen? Because I don't think, for example, in Chile, we're going to not build any more reservoirs.
Mm-hmm.
So once they are there, they will be there, and I don't think there will be more. So you just wanted to look the effect of them in the past and not thinking about the future.
But also in the future that influences, because when the reservoir is full and it stops working, there is also an effect. So this carbon that is storage there, it can be released to the atmosphere, for example, because it's not a stable place anymore. So it is important to study what happened also when these dams are decommissioned.
Ah, okay, so you're going to look at the prevention of the dams as well.
Yes.
Okay, the life cycle of the dam.
That's the idea.
Ah, okay. Okay, great, thank you.
Thank you.
There is a question in the chat.
Yes.
Dani Sebastián Echeverría says hi. And the question is, how are you considering the effect of reservoirs in the carbon burial rate across ecosystems?
Mm-hmm. Yeah. The reservoirs will be considered as another one of the ecosystem types. And I'm not sure about what do you mean, how, but they will be the receptors of carbon from the terrestrial system or river or whatever is upstream. Then you will have processes happening. You will model those processes inside the dam, the reservoir. So you will know how much of this carbon which enters will stay and will be buried, and assumptions, of course. And then you will see how much will be released. And then you will run this for years, and you will see how the sediments is going to be accumulated and how this is going to affect the carbon sequestration. If this is going to be needed. Hopefully, at some point, we can also include, for example, the changes in water level in the dam, because this will also influence the carbon emissions. I don't know if that passes you.
Apparently, yes.
Yes, I think so, yeah.
All right. So if there are no further questions, thank you very much, Daniela, for your time, for being here. That's it. Thank you very much. And we'll be announcing an upcoming seminar very soon. Have everybody a wonderful afternoon.
Thank you, everyone.